restart this. Again, this is the second part of chapter 32. We need to finish this chapter today. We're going to discover a very good tool, namely a pointing vector. And we're going to be using it to basically calculate the, it's going to be critical for your homework, basically in exam 2, because you're going to be using it to calculate the rate at which power basically is being dumped on a given surface, okay? So that's the intensity, really. That's what it is. The average of the pointing vector is the intensity. It also helps us in understanding solar sailing, because we're going to calculate also the pressure exerted on a reflective material, or also an absorbing material. So this will be the end of the class, basically, the last parts of it. But before I do that, there is actually a little bit of clarification that I need to capture from before, because what we did so far, we took Maxwell's equations and we took them in the integral form, actually, and we solved them in free space. So that's basically in a nutshell what we did. So we said, okay, I have these equations, and I'm going to write them now in actually not integral form, but rather in a differential form. So what happened in here? Why is it? Oh, because I don't have this selected. So basically, the divergence theorem, basically for the Gauss's law, basically for the electric field, states that the divergence of the electric field in this situation is equal to 0. Normally, it's not equal to 0. Normally, in a space where you have charges and you have a given distribution of charge, it's given by rho over epsilon naught, where rho is the charge distribution. However, we are in free space still, so rho is 0. So this is equation 1. The second equation we needed was actually the divergence of the magnetic field is equal to 0. In other words, the magnetic field never diverges. Divergence, and this is true no matter where you are, whether you are in free space or you are actually near current. It doesn't matter, because the magnetic field always circulates. And this indicates the fact that there are no monopoles. Had there been monopoles, okay, monopoles, then this situation will not be true. Then you could basically tally north poles by themselves and tally south poles by themselves and add them. And since theoretically at that point you could have some by themselves, you could end up with a net number of north poles by themselves or a net number of south poles by themselves as basically the difference between the two. But this situation is not possible. Therefore, always this is true, okay? So Gauss's law for a magnetism is always easy, okay? It always says that the divergence of the magnetic field is 0, okay? Then we discovered basically another law, namely Faraday's Lens Law, which I'm writing next. And Faraday's Lens Law, we discovered it last, actually. We said that the curl, basically, of the electric field, in other words, the EMF, okay, that goes around a closed path, okay, is simply the rate at which the current is the magnetic field is changing with time. Okay, again, this is a localized version of it, so we really don't care about the flux in this case. We're over closed surface, over a big surface, because we're just looking at a tiny point in space. So at this point, the area will cancel from both sides. This, to get to this versions of the Gauss's law, we really have to use Green's theorem or Gauss's theorem, okay, to do that, to go from the integral form to the differential form. For the circulation, you use something else called the Stokes Theorem, okay, to get into the differential form. But it's not really hard. We did it last time with the integral form, and we were able to get to this very same form too, okay? So this is nothing but Faraday Lens Law. Remember, Lens contribution was that minus sign, okay? The minus in it. And then the last law that we came up and corrected, actually we discovered it before, namely Ampere's law, but then Maxwell came in and basically fixed it. And that gives me the curl, basically, of the magnetic field, the fact that the magnetic field is created by currents. But I'm in free space, so I really don't have any currents. So the only thing that could do that then is a changing of the flux of the electric field. But since I'm in a local point in here, so it's going to just be the rate at which the electric field is changing with time. Oops. only a single derivative. So this is, again, technically, I should add really mu naught J to this expression. But again, I'm in free space, so there are no currents or current densities. So in this point, this is how Maxwell's equations would look like in the differential form. Okay. I'm going to go back to the same situation as we were before last time on Monday and state the following. I'm going to look for a solution of this form that the electric field only depends, and this is exactly what we did last time in the integral form, depends only on one coordinate in space, x, okay? It could depend on time too, and that is the whole point of it. So in other words, any derivative with respect to y or any derivative with respect to z of this electric field is 0 because there is no y or z dependency in it. And then in the same time, I'm going to take the magnetic field to be also in the same direction so that it's only depends on one coordinate. In other words, I suspect that these two are related, as we saw last time, and they are. Of the magnetic field also is 0. So there is no y dependency, there is no z dependency. If you say, okay, you know what, this electromagnetic, this electric field and the magnetic field, they're really not in the x direction, but rather they're in the y direction. So all you have to do is take your coordinate system and rotate it around the z-axis. And then the x becomes a y, and the y shifts to the minus x, and you're good. But you say, you know what, it's not it's not the y-axis, or it's not the x-axis, it's some axis in space. You can rotate your reference frame to one position and then rotate it in another position and bring it back so that that's your x-axis. One of the things that I'm not sure if you did or did not do when you introduced vectors in physics 4a, and that is vectors have this property that their length is invariant, doesn't change with rotations, okay? So the fact that we're arguing that this depends only on x direction, it could be any direction you choose because the length or the strength of the electric field and the strength of the magnetic field will not be impacted by these successive rotations to bring back the direction with which the solution is traveling to the x-axis. In other words, here is a source, okay, of light. And if I'm standing in here, I can call this is the x direction. If I'm standing in here, this would be my x direction. So basically, that is the point I'm trying to say in here. So physically, what it means is the star is far away. That direction between us and the star is the x-axis, okay? So call it the x-axis. If you make a different system of reference and you choose to happen that some axis that is not necessarily the x-axis because you were working with another thing, well, do the rotations. The strength of the electric field and the strength of the magnetic field will not change in the rotations. As a matter of fact, this is actually the definition of vector. Modern definition of vector state that a vector magnitude, remember a vector has direction and magnitude. Its magnitude, I mean, direction changes, but the magnitude does not change. In other words, the word used in modern physics is invariant. If you took relativity, and you're going to take it probably in the future, this invariance becomes very, very important in your studies. So that does not change with rotation. Okay? So that's why this is not really restrictive in a sense that putting it in the x direction, you're saying, wait a minute, you're putting too much constraint on this in Maxwell's equations. No, okay? Assuming that this is true, so this is not assuming that because of this fact, it's not a restriction really. Still, the advantage of doing it this way, the math looks a lot easier to handle, okay? So let's look equation 1, this equation in here, and how it looks like. Remember, the curl now, or the operation derivative with respect to space, only has one component, which is the derivative with respect to x. And this operator is really the derivation with respect to x in the x direction, plus the derivation with respect to y. in the j direction plus the derivation with respect to z in the k hat direction. But this is 0 for both the electric field and the magnetic field, and this is 0 for both the electric field and the magnetic field. So this expression in here, the dot product of this vector by this vector will just give me the derivative of E in the x direction with respect to x equals to 0. So that's what equation 1 yields. So it's a lot easier than this expression, because this is a dot product. E has 3 components, Ex, Ey, Ez. This vector has 3 components, derivative with respect to x, and derivative with respect to y, and derivative with respect to z. So at the end, the other 2 derivatives are 0 because there is no derivation with respect to y and z. Both the y component of the electric field and the z component of the electric field do not also, because the entire electric field does not depend on the y and z. So in this case, those derivatives are 0, so the only derivative that remains is this one. And the same thing for the second equation, by the way, it's also going to give me the same thing. The derivative of by with respect to y is 0 because there is no y dependency. The derivative of bz with respect to z is also 0 because there is no z dependency. The only thing that is going to remain from the second equation also of Maxwell is the derivative of bx, with respect to x also equal to 0. So those are the first 2 equations of Maxwell. They become very, very easy in this approach, okay? Having just an x and t dependency with no y and z. Well, this means if you take the entire derivative that Ex is constant with respect to x. With respect to x. And that constant better be 0. Same thing, by the way, Bx in here is constant with respect to x. Because when you take its derivative, it could have a time dependency, but that's not the issue in here. The issue is the integration with respect to space. I mean, when you say take a derivative equal to 0, you know that the entire derivative is constant, except in here we are dealing with function that can depend on 2 variables. Now, here is the trick. We are in a point in space. Right now I'm here. When I turned the light, there was no basically electric field or magnetic field in this point. So the disturbance must travel in here. Before this point, it was 0. When the disturbance traveled to this point, it's going to create a disturbance in such a way that the electric field is continuous. So it was 0, and it has to be constant. So the only value for it has to be 0. So Ex then must be 0 because of this constraint. So that is the only acceptable value. Because we are far removed from any disturbance. We are far removed from the source in here. So there should not be any native electric field in here by itself, unless the disturbance comes in. And if it does, then it will not have an electric component in here in the x direction, because its derivative is always constant, even if the disturbance reaches that point. So it has to remain constant. Since it was 0 before, it has to stay 0 after. So that's the argument for the Ex equal to 0. And the same thing actually for Bx equals to 0. Because there was no electric field or no magnetic field. We are far away from any source for them. And now the disturbances reaches us. And it reaches us so that the derivatives with respect to x and for both the electric field and magnetic field are 0. In other words, it doesn't change them. So if they were 0, they stay 0. Is this point clear? Why the electric field in the x direction and the magnetic field in the x direction is 0, just because of this constraint. So the first 2 equations of Maxwell in this approach, if I take a disturbance that travels in a direction, which I call the x direction, and it shows my Cartesian coordinate system accordingly, they don't change. The derivatives from the first 2 equations are 0. So what that means is that the disturbance, once it reaches this point, it doesn't change them. Since they were 0 before, and the disturbances reaches them so that the derivative stays 0, that means they stay 0. Do you guys understand the point or not? Yes, no? Okay, very good. So that is really why there is no component now for the electric. So in other words, here is, let me redraw the picture a little bit so that we're see what we're saying in here. So we have an electric field. I didn't make any generalization on this electric field other than the fact that this electric field does not depend on anything but the x direction and y direction. And the same thing. So this is the direction of x and t. This is direction of x and t. And we're in this direction. So this is the x direction. As the disturbance reaches this point, so it was here before. As it reaches this point x in space, okay, it does not have an x component. So it does not have it in here either. So it does not have it anywhere in space once it reaches that point. So Ex is equal to 0. Same thing, by the way, for the magnetic field. Bx is equal to 0. So whatever is happening on a plane perpendicular to the plane of propagation, where the direction is moving. So that says what the planar solution meant, really. So that's why this disturbances are transverse. These waves, as they're coming from the other side, they are going to be transverse. They are going to actually be perpendicular to the direction of propagation. So what is going on? This is where it's moving with no components in this direction. So if there is any, it's going to be in the other directions, namely the y direction and or the z direction. At this point, there is no restrictions on it. So namely, basically what we ended up with then is the electric field looks like this then. The electric field is a vector that has 0 components in the x direction, but has a y component in the y direction and may have z components in the z direction. And so is the magnetic field, by the way. It has also components in the y direction and in the z direction, but no component in the direction where we have decided that it's moving. In other words, Ey still is a function of x and t. And the same thing is for all of these variables, basically. If I write them down, it's going to be Ez is some function of x and t. And the same thing for By, it's a function of x and t. And Bz, finally, is a function of also x and t, okay? So that is basically what the first 2 equations are telling you. The first 2 equations are telling you basically that this is a transverse operation. So whatever it's happening, it's not happening in the let me look at the other 2 equations basically, namely Faraday Lens Law and also Maxwell enhanced with Ampere enhanced with Maxwell. So the first one states the following: that the curl, remember the curl from your math class and physics for A2, okay, was now the derivatives with respect to x is fine. There is no derivative with respect to y. There is no derivative with respect to z because there is no y and z dependency. The first expression involves the electric field. The first expression, Faraday Lens Law, involves the electric field. The electric field has no components along the x direction. Has a component, potential component along the y direction, and a potential component along the z direction. This is equal to minus the derivative with respect to time of the magnetic field. The magnetic field has no x component, but has a y component and a z component. So this is how Faraday Lens Law look like. The x direction, first of all, if I take the x direction, I have 0 times Ez is 0. 0 minus Ey is 0 is equal to minus the derivative of 0. So this checks in the y direction. So the first 2 equations confirm this equation in the x direction. How about the y and the z component directions? Well, this equation, I have to write it as follows. First of all, for the y direction, I have to cancel this too. Remember, you guys, the rules for that. So it's minus the derivative of Ez with respect to x equals to minus the derivative of, remember, I'm doing it in the y direction, By with respect to t. So this is the y component. I cancel the j hat, the k hat from both sides. So this is equation, I don't know, I lost numbering track of these things, but I'm going to give it number 1, capital, basically, numeral 1. I'm going to do the same expression here, but it's going to be in the z direction. In the z direction is going to be this straight out derivative with no minus is equal to minus with this one. So the minus and the minus cancel, by the way, in here. But in the second one, it's not going to cancel. It's going to stay. So the second equation will give me the derivative of EZ with respect to x is equal to minus the derivative of, I'm sorry, not EZ. This is not correct. Because remember, it's a derivative of EY in here. So this is y, and this is going to be BZ with respect to t. So this is equation number 2. I'm going to just write the equations and discuss the solution without going in depth into finding solutions. But the point being in here also is that I'm going to do the last equation, which is this one, in the same fashion. But instead of doing curl of E, we're going to do curl of B, actually. So we have an I hat, J hat, K hat. I have the derivative with respect to X only. There is no derivative with respect to Y and Z. The magnetic field only has components in the Y direction and Z direction, no components in the X direction, is equal to mu naught, epsilon naught, the derivative with respect to time of 0 EY, EZ. So again, we're going to write these equations straight out. Again, in the Z direction, in the X direction, I will have 0 times BZ minus 0 times BY, that's 0, is equal to mu naught epsilon naught derivative of 0, which is 0. So that checks immediately. The Y direction, I will have a minus the derivative with respect to of BZ with respect to X is equal to mu naught epsilon naught times the derivative of EY with respect to T. This will be equation number 3. And with respect to X, in the K hat direction, in the K hat direction, there is no minus, so it's going to be straight out positive. So it's going to be a positive. The derivative of BY with respect to X is equal to mu naught epsilon naught, the derivative of EZ with respect to time. These are the 4 equations of Maxwell now. This is basically what is left of them, actually, is this 4 equations. If you follow the following rationale, and I'm going to leave it up to you to do it. If you say the following then, that EY is some E max in the Y direction times cosine of K times X minus CT, and EZ is the same thing basically. So let me rewrite it more succinctly. Okay. E as a vector is going to be simply 0 EY in max in the, or it doesn't matter the notation, EZ max times cosine of K times X minus CT. Okay. And if you do the same thing, by the way, for the magnetic field, 0 again, BY max. Those are constants, by the way, and BZ max, there's just the amplitude of this waves times cosine of K times X minus CT. If you do this, what you will find is, first of all, and you square and you find E in magnitude and B in magnitude, you will find the same result as we found last time, namely that the B as a whole, which is the square root of basically B max, so this is B max. So it's going to be BY max squared plus BZ max squared plus 0 squared if you care to write the X component because it's 0. This will be equal to basically E max, which is the same definition, by the way, just the Pythagorean theorem in here, divided by C. So this result is true, even in this situation. So in other words, the maximum of the magnetic field is always 1 over C, that of the electric field. That's one result. The second result that you're going to do is, if you do the dot product of E times B, you will end up with 0, using these expressions themselves. Namely, this one, this one, this one, and this one, and combining it with this basically values for E and B by just taking the derivatives, because all you have to do is take the derivative with respect to Y, and Z in all of them. And again, the reason why I wrote it this one is because, again, I can take this equation 1 and combine it with equation 4 and take the derivative of with respect to time of one of them and the derivative of the respect to position with respect to the other one. I will get rid of the cross derivatives and I will end up with a wave equation for one component. I do the other derivatives and I cancel the cross derivatives and I will find a wave equation for the second component. I take equation 2 and equation 3 and do the same trick. Each and every one of these components, namely By and Bz and Ey and Ez, is actually a part of a wave. The combination of them is actually a wave. So it goes back to the wave equation from the previous chapter. That's why I wrote them in this harmonic form. Okay. So what this is saying is the following, that as the electric field now has two components, not necessarily in the y direction, and as the magnetic field now has two components, they remain perpendicular to one another. As the electric field can spin one way, the magnetic field will spin with it. So this is the general form of an EM wave. The direction of E, of the electric field that is the polarization. So the solution that we did last time was polarized in the y direction. That's last time. But in general, it doesn't have to be. It could be polarized in any direction. So what you do in this case, you run filters and basically absorb all of the radiation that goes through except the one that you like to have it. And that's how polarizers work, actually. That is exactly how they work. So as a matter of fact, this will be some sort of if the Emax in the y direction is equal to Emax in the z direction, if these two magnitudes are the same, and it's possible for them to be the same, then you have what is known as circular polarization because both of them have the same magnitude. If one of them is different than the other, you have elliptical polarization. So yeah, they will be polarized in a different, so that their magnitudes are not the same. And as they do, those of the magnetic field also, they will move accordingly too, because the magnetic field are related to this expression, to the electric field. So we don't care really for the magnetic field when it comes to polarization, because one of them will tell us the other, number one. Number two, as I said before, because of this relationship, the intensity of the magnetic field is usually not, we don't talk about it when it comes to these points. So I hope I made the general case in here. I'm relying on you guys to continue the calculation. Calculations are a little bit tedious and long, but they prove the same points in here, except now we're getting into the more general form of these equations and how they look like. That's the only thing that is different from that. So the harmonic solution is good. So here is the point. We have a wave now. We know that they are waves and they travel and so on and so forth. The question of the day now is the energy. We know from previous chapters that the electric field carries with it an amount of energy. The energy density due to the electric field, if you guys remember from our discussions from before, was 1/2 of epsilon naught times the electric field squared. The energy, that of the magnetic field, the B field, we found it to be 1/2 of B squared divided by mu naught. So those are the results we found a long time ago. We already found today, and last time, that B and E are related to one another through this expression, where C is equal to 1 over square root of mu naught and epsilon naught. So those are the results we found so far in this chapter, okay? This B is actually the maximum values, not the instantaneous values. But since the instantaneous values are in sync, so this is true all the time too, even for the instantaneous values, okay? So these are the results that we have found. So let's find the total energy for an EM wave. Well, then it's easy. The energy density for the total wave. So energy density, okay, what I mean in here is joules per per meter cubed, okay? So in this case, it's just the sum of the two. So it's going to be 1/2 times epsilon naught times E squared plus 1/2 times B squared divided by mu naught. That's the only thing that is basic. But remember this expression, B squared is equal to E squared over C. B squared is equal to E squared over C squared. And 1 over C squared is equal to mu naught epsilon naught. 1 over C squared actually is mu naught epsilon naught. So this expression then, this is the EM wave, by the way. This is the total, both of them. So the expression for the energy density for an EM wave then is the one from the first one for the electric field plus the one from the magnetic field, which is just 1/2 times divided by 2 mu naught times B squared. And B squared is E squared times this number. B squared is mu naught epsilon naught times E squared. This is exactly what B squared is. Because remember, 1 over C is the square root. So when you square it, it's going to be square root of mu naught epsilon naught. So that's what we have found. Cancel the mu naught in here and the mu naught in here, and these two expressions are identical. So the contribution of the magnetic field is the same when it comes to energy. The magnetic field contributes the same as the E field when it comes to energy. So that's something. Yes, the magnitude and sensitivity and equipment and how much sensitive it's going to be the electric field that's going to give you all the readings. But when it comes to energy, the one that you transmit and your phone will receive and convert, both of them will give are 100% equal partners. As a matter of fact, the total one, the 1/2 and the 1/2 becomes just 1, is just epsilon naught times E squared. That's all. So this is the total energy density. If you like, you can write it as, because E squared is just 1 over, it's equal to C times, so you can write it as B squared over mu naught. It's the same thing. It's the same expression. Okay, just by following the same rationale in here, where E squared is C squared B squared, and C squared is 1 over mu naught epsilon naught. The epsilon naught cancels the epsilon naught, and you'll be left with this expression. So this is the energy, the total energy density. As a matter of fact, there is another way of rewriting it that is probably a little bit more convenient, and it's this one, involving the two products, just to show in between them. Because remember, I just found to be epsilon naught times E squared. What we usually write it with is the fact that this. Sorry, I don't know what happened. Can everybody hear me now? Okay, thank you. I don't know where we stopped, but for some reason, I realized I was talking to myself. So basically, like I said, this expression, usually we don't try to write it as such. We write B or E as itself as CB. So this will be as C times B, one of the E's in here. And we leave the other one just to show that both of them are equally contributing. And so this one, remember, 1 over C, or C is equal to 1 over square root of mu naught epsilon naught. So this will be actually square root of epsilon naught divided by mu naught times E times B. Okay, so these are different ways of writing the energy density. Okay, another important component in here is to really find the average of this energy density. Okay, so the average of the energy density will be important for us right now. So again, I'm just going to take E to be some maximum value cosine of k times x minus ct. And b is going to follow the same thing, b max times cosine of kx minus omega ct. It doesn't matter which expression I write at this point. If I write it in this form, it's the same thing as writing in this form or in this one. So all of them are there identical. So if I find the energy density in here, because the reason why we're after this one is because the frequencies in here are so high. That means the periods are very, very short. So we really care about the average more than anything else. So the average of the energy density is going to be equal to, again, I'm going to take this one, epsilon naught squared, epsilon naught squared times E max squared times the cosine of k times x minus ct squared. The cosine squared, there is an identity, if you guys remember, cos or cos squared minus 1 is equal to cos squared minus sine squared is equal to cosine of twice the angle, which means that 2 cosine squared minus 1 is equal to cosine twice the angle. Move the numbers around. So this is cos squared of any angle, it doesn't matter which one. So I'm going to write this one, x minus ct is equal to, it's going to be equal to 1 when we move it to the other side. I'm trying to write it out of memory, but it doesn't matter because the other one is going to be 0 anyway when we average it, divided by 2. When I average this expression, this is how the cos squared would look like. Okay, it's always positive, by the way. It's always positive, okay? Because it's cos squared. I'm talking about this version of it. It should give me a value somewhere in between, which is going to be exactly 1/2. In other words, the average is going to be exactly this 1/2, and the average of cosine of twice the angle is going to be this function, okay? Sometimes it's positive, sometimes it's negative, sometimes it's positive, sometimes it's negative, and the positive and the negative will cancel in each period. Since I'm taking a very large amount of periods, then in this case, they're going to all cancel. As a matter of fact, we can go back and do the actual integral and find it to be 0. So the average is equal to 1 over t. Remember when we did the RMS a long time ago? The root mean square, this is identical. So the integral from 0 to t of this cosine squared of kx minus ct, and I'm going to average it over time, and it doesn't matter really, where t is related to omega and t is equal to 2 pi over omega, and omega, if you remember, is equal to kc, so it's going to be 2 pi over kc, okay? So if I do that, and I'm going to find this integral equal to that expression, and the integration in here is going to be from 0 to some even number of pi, and it's going to give me a sine. The integral of a cosine is going to be a sine, and the integral of the value of 0 is going to be 0. Sine of 0 for the whole argument in here is going to be 0, and sine of the period is going to be the same value. It's not necessarily going to be 0, by the way. It's going to be sine of 2kx, okay, whatever x is. And when you go a period later, actually you're going to go 2 times the period because of this factor 2. So you're going to go twice the period. So you're going to add 4 pi to the to 2kx, and cosine of, a sine of 2kx and a sine of 2kx at the end, they will cancel. In other words, whatever the value in here in space is going to be repeated after 2 periods, and you're subtracting this value from that value is going to give you 0. However, this 1/2 will not give you 0. This 1/2 will definitely give you 1/2, okay, when you average it with this integral, because all you're doing is 1 over t, the integral of 1/2 of dt between 0 and t, and 1/2 is constant, so it's going to be t over 2, which is 1, so it's going to give you 1/2 basically times 1. And this portion in here will give you 0. And that's basically how you find the average in this situation. We average it over time, but it doesn't matter really if we did it over space, it's going to give you the same result. But the definition over the for the averaging over a period is going to be 1 over lambda, though the integral from 0 to lambda of the same expression, kx minus CT for dx now, and you do the average, and here noting that lambda is related to k via this expression, 2 pi over k. Okay, the wave number and the wavelength are related to one another via this expression. If you do that, you're going to end up with the same situation. Again, you're going to end up with when x is equal to 0, so it's going to be left with the sine of this thing, okay, sine of twice this thing, and plus 2 periods. So whatever that is value in here is going to be identical to this value. You subtract the 2, and you're going to end up with 0. So again, at that point, the only average that's going to remain is that of 1/2, because the integration over 1 over lambda from 0 to lambda of 1/2 dx is going to give you, again, lambda over lambda cancel, and you're going to be 1 times 1/2, which is exactly 1/2. In other words, this average is going to be 1/2. So there is, whether you do it over space or time, it's going to be the same thing, because again, wavelength in this case is also very short. Okay, so just wait at least whole wavelength and you're going to be fine. So the energy then, when you average it, the energy density of the EM in this case is going to be 1/2 of epsilon E max squared. Okay, so this is basically how we can write it. Let me write it back into this form again. Square root of mu naught epsilon naught times EB. And this is really what was a hint to Mr. So we have 1/2 of square root of epsilon naught over mu naught times E times B. Max, of course, because we did the average already. Okay. So Mr. Pointing defined the following vector. John Pointing, okay, because I was confused the first time I heard about it, and everybody who hears about it, I tell you it's not a typo. It's supposed to be like this. So what does this vector does? They define the vector S, and the vector S by definition is equal to E cross B divided by mu naught. Okay, did I define it correctly or not? Let me check my the class that we did. Yeah, that's exactly how we did it in the points. I mean, I'm looking at the notes from the. Remember, every chapter has a summary, so I'm looking at the summary. So this is Pointing vector. So this is by definition. Remember, the electric field is this way, the magnetic field is this way. And if you do the right-hand rule, basically E cross B, it points in the direction of propagation of the wave. So this is where it moves, propagates. So Pointing vector points towards the direction of propagation of the wave, of the EM wave. There was no basically pun intended, but it's really exactly how it works, okay? So when he defined it, I guess he was too excited to define it that way. But that's really what it does. Furthermore, if I found its value in here, S, using the right-hand rule, it's going to give me E times B, because both of them are perpendicular to one another, by the way. I just argued earlier from the previous analysis for planar waves that these are going to be perpendicular. So its magnitude is going to be just mu naught. And again, if I average this expression, S bar is going to be E max, B max, divided by 2 times mu naught. So when you average it, the 2 comes into the equation. Again, for the same reason I was arguing earlier for it. Okay. So this part of the energy density then is related to that. So that's all there is to it then. So the energy density is related to that. Let's talk about the amount of actually energy that passes through a certain point. So I have, let's say for example, I have 1 meter squared. Okay. So I have an area in here, okay? And if I wait 1 second, this area will be crossed by this much volume of electromagnetic waves. After 1 second, there is a C times 1 second. In general, C times delta T that passes in delta T amount of time through a cross-section A. So the energy in this volume that passes is going to be the energy density U, sorry, not lowercase u, I meant U, capital U, is going to be the energy density times the volume, and the volume is A times C times dt. This is the amount of energy that passes in dt amount of time. So the power then is going to be simply, so this is the power, is going to be du over dt. And that's U times A. Okay? So the average power, again, if I'm interested in the average power on average, so this is how much power is going to pass through. It's always carried, at least for a unit area A. So it's going to be A times, of course, I have to collect it in a given area in this case, A times the average energy. So all of these things are related in this situation. All of this analysis is related. Okay? In other words, I can define the intensity now, intensity I, as being the average power divided by the area. So this is in watts. This is in meters squared. So this is the intensity by definition. Okay? So the intensity is really U bar. So all I was calculating all along in this case is just U bar. So that is the average, that's the intensity, which is the average energy that passes through a square meter per unit time. So that is the whole thing in here. So this is the intensity, which is the average EM wave energy passing through 1 square meter per second. When I say that, I mean it's power, okay? Energy per unit second is really the power, okay? So this is in a nutshell basically what we've been dealing with. Now, as related to power Poynting vector is E max B max divided by 2 mu naught, and that's exactly how also the expression for U of bar is. So let's write them together next to one another and see exactly how they're related. So we have S bar is E max B max over 2 mu naught. That's one. We have the intensity, which is really U bar. The intensity as equal to 1/2 square root of epsilon naught over mu naught times E max B max. If I multiply the denominator and the numerator by square root of mu naught, then this expression then becomes I, the intensity, which is in watts per meter squared, by the way. Okay, that's a unit for it. Watt per meter squared is 1/2 of square root of mu naught epsilon naught times E max B max divided by square root of mu naught squared, which is going to be mu naught. So basically, this part now is exactly Poynting vector average, and this part is 1/c. So I, the intensity, is the average of Poynting vector divided by c. That's an important result for your homework, for your exams, for everything. So once you find the Poynting vector, all you have to do is divide it by c, and you know what the intensity of the wave is. So if they make a laser, and there are a lot of problems in the homework for lasers, and they tell you how many watts it has, okay, then you know basically if it reaches a certain sphere, that is actually what the intensity of that beam is. And since you know what the intensity of the beam is, you can find what S bar is. And since you know what S bar is, you can use this expression to find, because remember, B max and C max and E max are related to one another. This expression is the same thing as E max squared divided by 2 mu naught C, because B max is just E max over C. So if you know S bar, you can find what E max is, what the electric field is in magnitude, what the maximum electric field is. And same thing, if you want to, you could use the same expression by finding it as C times B max squared divided by 2 mu naught. Mu naught is constant, C is constant, so everybody is constant. So if you know, again, the intensity of the laser beam, for example, and you know where it's going to reach, so you're going to find S bar at that point, because all you do in this case is the wattage that is given to you, divided by meter squared, by the way. You have to know how far you are in order to shine the laser. Then you're fine. Then you know what the watts per meter squared are. And at that point, you can find the strength of the electric field is. Okay. For example, the radiation coming from the sun is 1,200 watts per meter squared that will hit it on every second on Earth. From there, you have the intensity I. You can find from there, multiplied by C, you have S bar, and you're in business. Then you can find what the electric field is, what the magnetic field is coming from the sun, and all of that. So you can do all kind of calculations at this point. So those are your tricks for doing stuff like this one. There is one final point in here, and that is related to the radiation pressure. Okay, the actual argument for it is due to Maxwell, Mr. Maxwell himself, and modern physics that deals with the electromagnetic fields in continuous media will give you a better rationale for it. Here is the argument he made. You have a material. You have two kinds of materials. You have opaque materials, and you have reflective material or transparent. What am I saying here? Opaque, basically absorbing materials, or reflective materials. I should use the word in here, absorbing materials. Okay. So a material that absorbs radiation, you hit it with radiation, it doesn't matter which one, and absorb the whole thing. Okay. Does not reflect anything off of it. So in this case, he argued the following, that there is a momentum imparted to it by the electromagnetic radiation. At that time, there was no quantum mechanics or anything like that. Modern physics gives you a better explanation for this. He says that the momentum that it's going to impart it to it. So this is the momentum now. There are so many P's in this class today. There is the momentum. There is already the power, and there is another one that's going to come shortly, namely the pressure. So that this is the day of the 3 P's. So the momentum P, I usually do give it a hat in here to make distinction between the other two. So the momentum in this case is going to be related to how much energy is imparted to the material by the radiation that hits it on average, okay, divided by C. So this is the expression for an absorbing material. For a material that reflects completely, because it's hit by the radiation bounces off of it. It's like, even if it bounces off of it, it's like the recoil of the gun. When you shoot a gun, for example, the bullet will travel in one way and the gun will hit you back. So there is a recoil in the reflective materials, and he just added it to the same value. So this is the momentum in that situation is going to be twice as much, because it's going to absorb, take it in, and then throw it back. So the absorption is going to be here, plus the recoil, the motion that is going to be given to that. So this is basically the argument he made. That is the essence of the whole thing. Now, if a material, normal material, it's not 100% absorbent, it's not 100% reflective. So there is a fraction of absorption versus that of reflection. So this fraction, I'm going to use the symbol FR for it. So FR in here stands for the fraction of reflected EM wave. Okay. So in this case, then, if it reflects some and absorbs some, then the actual expression for the momentum is going to be delta P in this case, momentum again, that is imparted to the material, is going to be 1 because of the total absorption. Is going to be hit anyway. It's going to hit it no matter what. Some of it will be reflected times delta U over C. So this is the general expression. FR is 0 for reflective materials. for absorbing materials. Absorbing materials. So materials that absorb everything 100% gives you 0 fraction reflected. Materials that are 100% reflective, this is what they are. These are reflective, 100% that is reflective materials. Obviously, as I said, these are two ideal situations. It doesn't matter which object you're talking about, they always have a certain amount absorbed and a certain amount reflective, okay? So this expression is more general. So when you're careful, this is the expression that you're going to use. So in either case, he argued then the exert of force, which is delta P, momentum, over delta T, this is F equals to ma, if you guys remember from physics for A. Except when you express A in terms of derivative with respect to time, and you take the d with respect to T of md, this is exactly what that expression is. So F is equal to the ratio, rate at which the momentum is changing. The only trouble with this is we're talking about an electromagnetic wave that does not have mass. So this expression in here is kind of nonsense in here for us. But that's the analogy if you wish to express it. But it's still, if you're dealing with momentum, you can take a rate at which you're changing, that is the force. Even in modern physics, even in Newtonian and Einstein physics or that of quantum mechanics, so you can always argue that, okay? So it's related to the momentum. So the rate at which the momentum is changing. So again, it doesn't matter which material I'm going to take. I'm going to take one that is a little bit more general, is the rate at which the energy is being delivered divided by C. And that is the power. Okay. And the power, if you remember from the previous analysis, the average power times the area is actually the intensity, or the intensity times the area is the average power. So again, we're back into the same situation now. We can find the momentum. We can find the force that is exerted on the material itself. Okay. So this is the power, and the power is related to this expression in here. One more expression and we're done with this. Namely, the force divided by area, if you guys remember, is the pressure. That is why I said this is the day of the 3 P's. You have power, you have momentum, and you have now pressure, and they all use the same symbol. So I'm trying to distinguish between them in here, hopefully that you're not confused and you know exactly what you're talking about. This is F over A. That's pressure over area, so force over area, so that's the pressure. Delta P over delta T, that is actually the force, the rate at which the momentum is changing. And the rate at which energy is delivered, that is power. So that's, hopefully you guys can see I mean, this is a class 4B, so this is a calc-based course. So I'm hoping that you guys have that sense of there is clear distinction between all of these things in here. This is measured in Pascal. This is measured in kilogram meter per second, and this is measured in watts. So the units are completely different. They are not related, although the symbols are somewhat connected. Okay, and I'm using the MOM under P mom for momentum, P hour for power, and P pressure for this one in here, just to make this distinction clear. Okay, so this is going to be 1 plus, again, I'm taking the general case, I'm not taking totally absorbing or totally reflective materials, is going to be the rate at which the power is divided by A divided by C. And the power per area is the intensity. The power per area is the intensity, which is U bar. And the intensity is S bar over C, okay? Do you have an extra C in here? Did I have an extra C in here? I think there is a mistake in here. I think they made a mistake in here. Did I? This looks correct. S bar over C. Again, let me check the notes from the class. No, that's correct. Everything is correct so far. S over C. Okay, I think there is probably, I'm off with a factor of C now, because I'm looking for it, but I'm hoping to find where that C went. Okay. Because this pressure should be just S bar over C, and I'm seeing it now being S bar over C squared in here. Because this is the intensity, the power over A, and the power over A. Oh, sorry, that's I. That's I. I'm correct. Okay, this is correct. I'm sorry. So this is I. This is the intensity. So everything is all good. There is no problem. So this is 1 over FR times I over C, and I is the average pointing vector. Okay, so everything is all good. For a second, I thought we went south. Okay, so this expression is good. Okay, so S bar over C. So again, finding that pointing vector will tell you how much pressure you have. One of its applications is the solar sailing. And actually, I think there was a Japanese project that was, I think it's still an ongoing project, trying to build some solar sails, because that's free energy that you get from the sun and continuously pushing your sails. Except the problem with it right now is that it requires tremendous amount of area to produce an acceleration bigger enough to have your basically rocket or your ship or whatever you're trying to build escape the pull of gravity of the sun. That's the only trouble with it. I think it has to be almost a meter, not a meter, a kilometer and a half squared, almost a mile squared, and a mile squared stretched from both sides. I mean, mile by a mile, so it's a mile squared on each side, so that it can sail and gain enough velocity to escape the pull, enough acceleration, I should say, to escape the pull of the sun and go completely interstellar, go and outside of the solar system. Okay, so this is the basis for the solar sailing. Obviously, it has other applications and other things, for example, and so this is not just one of the things that you're going to be focused on in here. There are a lot of the homework problems deal with this same issues. Okay, the bottom line is the following. Your pointing vector is defined above. What is it? Here. So most of the problems that you have, you're going to be dealing with pointing vector. The direction where the pointing vector is really the direction where the wave is traveling. So that is really meaningful too. So pointing vector points or is pointing in the direction of travel of the wave. Okay, and then that's one thing. Once you find it, you're in business. You can find a lot of things. You can find, first of all, the intensity of the wave. The intensity of the wave is actually the pointing vector. The intensity of the EM wave, it's the average of the pointing vector. Okay. Once you find that, you can find also the pressure. You can find the power. You can find everything in this one in here. So I hope that you guys. Because this is it, basically the entire content for this class. Okay, I'm gonna post this stuff later on in the day. I will be on Monday from same time when we're supposed to meet. Go through, if you have any questions about the review problems for exam 4 are going to be all of the homework problems basically that have been assigned so far from chapters 30, 31, and 32. Okay, so all of those, you need to go through them and make sure through with a comb and have an understanding of them. I'll be available again on Monday for you guys to discuss any of these problems and go through them, and we have to solve them if need be and all of that. Assignments are still due before the exams in terms of homework and other assignments. The exam is going to be actually on, I don't remember exactly how we did exam 3, but it's going to be the same time when exam 3 was offered, and it's going to be same time when exam 3 was ended. And I believe from the time of the class to sometime in the afternoon or something along these lines. So in other words, a week from today, you're supposed to be taking the exam. And oh, exam 3 was done on a Monday. Exam 2 is the one that was done on a Wednesday, if I remember. Okay. So anyway, we're going to do the exam in the same format because it's going to be on a Wednesday. So whatever format we did with the exams 1 and 2 on Wednesday, that's the format for exam 4. So we're not going to have a live class on Wednesday, week from today. We will have the final on Monday after. December 14th is going to be our final. And it's going to be in the same format as this exams again. The review for the final is going to be all of the exams that we did so far. In other words, review all of the problems that we did, everything, and make sure you're ready for that exam. And that's basically in a nutshell what everything is. Do not forget you also have a lab that is due. And I think the deadline for it is sometime early next week or something. And that's it. That's all the class there is to it. So that's all Physics 4B for you guys. Any questions? The final exam, I don't really know what the policy of the district is, but there will be more problems in it. So typically you've been experiencing 4 problems per exam. This exam usually, I think, not 8. I think I usually have about 10 problems or something like that in it. So it's a lot longer. So if it takes you 2.5 hours to do the previous exam, so you're going to count about 5 hours to do this exam. Okay. Plus another hour that I'm going to allow you so that you can scan your stuff and upload it. Okay. So again, I really don't remember how long, honestly. So Sebastian is asking for the final. In the past, I really don't know exactly, honestly, because this is my first time teaching in Norco, so I'll have to check exactly about the policy on that. So let me go back and get the exact time, and I'll get back to you, Sebastian, and hopefully you will have an answer way before the actual exam is given, where hopefully early next week you will have the answer to that. Does this make sense to you? Okay, no problem. So, but the exam 4 is the same format that we've been doing. I hopefully get. Don't forget also there is a quiz on the last 3 chapters. Chapter 30 and 31 and 32. And that quiz is due, I believe, on Monday. So that quiz is important too. So hopefully it's for us here. Okay, some people were confused last time. The quiz has nothing to do with the exam. I mean, it's supposed to prepare you for the exam, but it is not an alternative to exam, okay? So go ahead, take the quiz as soon as possible to help you prepare for the exam. But don't forget the exam is a different story altogether. Can I have a thumbs up from Faraz, at least the people who were confused last time with this thing? Got it? Okay, very good. So I'm going to stop the recording right now.